Hello. Today we're going to go through some of the elementary proof techniques. A lot of the theorems that you might prove in this class will take these forms. Let me jump right to it. Okay. So let me first tackle the ones where the theorem is structured like if P, then Q. So it's an implication where if P is true, that P is called the hypothesis, then some conclusion Q will be true. Okay. The direct method is when you want to prove something like this, you first assume the hypothesis is given to you. So P is true, so you could start that as a given situation, and then you use either like the definition of P or maybe equation given by P, and you manipulate it and see if you can do some mathematical deduction to arrive at the conclusion Q, or check the definition of Q. So an example of something like this is the following theorem. So if an integer is even, then its square is even. Okay. So this is one of those if-then implication format. So in this case, if you want to prove this using direct method, I assume that I have an integer that's even, and then from there, I want to assume that, I want to show that if you take that square of that, then it's even. All right, let's look at it. So the first step is to say that you have an integer that's even. So I'm going to give it a name. So when I introduce something like that, I use the word let. So let x equals to 2k be an even integer. So I'm using the definition for even integer here. If x is an even integer, then it could be written as 2 times some other integer. I named both of them in one line, right? So the x is the integer of interest in the statement of the theorem. And if it's even, it could be written as 2 times another integer. So k is the other integer. Okay, from here, I want to look at what the square is going to look like. So we're going to square both sides of that equation and then get x squared is equal to 4k squared. So when you square, you distribute the power to 2 squared, which is 4, and k squared is k squared. And once you have this, you can kind of rewrite it so it looks like it's 2 times another integer. So if k is an integer, then 2k squared is another integer. And the reason why we rewrote it this way is to show that the squared, x squared, is 2 times something else. I want to show that that's even, and that's the definition of it being an even number. So I've rewritten it so the square is multiple of 2. And that's another way of saying it's an even number. So x squared is an even number, and that's the end of proof. So we just took the hypothesis that's given and you try to manipulate that to get to the consequence of that implication. So I hope that made sense. Okay. All right, so how else would you be able to prove something like that? So the next structure, next method of proof is called contrapositive. So sometimes things get a little bit simpler if you phrase it as the opposite of the implication. So instead of saying P implies Q, that happens to be equivalent to not Q implies not P. Now, P implies Q is different from Q implies P. The direction of arrow matters, but when you flip the truthness of the Q, and say negation of the consequence implies the negation of the hypothesis that happens to be logically equivalent to P implies Q. So sometimes this is a more straightforward way to prove that. So if I want to, so this gives us a different technique to prove. So if I want to show P implies Q, instead of starting at the hypothesis, assume that the consequence doesn't hold. So assume that Q is false. And then from there, you work towards the hypothesis will also have to be false. And that would be equivalent to showing that P implies Q. Okay, so here's an example. It's a little bit contrived. So here's a statement of a theorem. So suppose A, B, and C are real numbers, and A is greater than B. So let's say that's given. If AC is less than or equal to BC, then C is either 0 or a negative number. Okay. So let's see if you can prove this using this contrapositive method. So this is the implication here. Everything before it is a setup. So I'm just going to copy the setup first. So suppose A, B, and C are real numbers, and A is greater than B. So that's the given setup, so I'm just going to write it down. Okay, so now instead of starting with AC is less than or equal to BC, what I'm going to start is the opposite of the consequence. So instead of saying C is less than or equal to 0, I'm going to let C be positive number. So that's the opposite of being less than or equal to 0. So if C is a positive number, then one of the axioms we did in the last chapter, multiplicative order law, says that if you multiply by a positive number, you can preserve the inequality. So we already have A is greater than B. If you multiply C to both sides, and if C is positive, then we get the inequality is preserved. AC is greater than BC. So just by one step, we can get to this conclusion. And notice this conclusion that we came to is the opposite of the hypothesis of the theorem statement. Right? The inequality is going the wrong way, and equality is not included. So we started with the opposite of the consequence, and then we ended with the opposite of the hypothesis. So what we just did is the proof of this implication. It's a little bit hard to wrap your head around at first, I think. But sometimes this is more straightforward thing to do. Okay. All right. Another method that we're going to discuss is what's called the method of contradiction, or sometimes called the indirect method. This is another logical equivalency. So if you want to show that P implies Q, remember the implication, the only way implication fails is if a true statement pointed towards a false statement. So another way to say that is that this is equivalent to the opposite, or the negation of P being true and Q being false, or not Q is true. So P and not Q. All right. So in this method, what you do is you assume the hypothesis. Assume P is true, and you also assume that the consequence doesn't hold. So P is true, but Q is false. So you assume both of these things at the same time, and then maybe you can manipulate these two statements and then obtain what's called the contradiction. So any statement that says something is true and false at the same time. So in logic, that's an impossible thing, conclusion to reach. If you get a contradiction, then you must have started with the wrong hypothesis. And the only thing you assumed, I presume, is these two things, P and not Q. So that assumption must have been wrong. If that assumption is wrong, that's the opposite of P implies Q. So that's how you can show that implication. I hope that made sense. So a short example where this technique makes sense is it doesn't exist but we did an example at the beginning of the chapter actually. So let me just kind of point you towards theorem 2.3 that we did at the beginning of the chapter. So if A, B, C are odd integers, then the quadratic equation ax squared plus bx plus c equals to 0 that has no solution in the set of rational numbers. So what we did in the proof, just a quick recap of what we did, is that we assumed A, B, C are all odd, and we also assumed that rational solution existed, this is the opposite of the consequence, and then somehow came to a conclusion that ax squared plus bx plus c had to be odd, and this cannot be equal to 0, which is even number, and odd at the same time. So that's a contradiction. Therefore, this implication holds. So that was the structure of the proof we tackled earlier. So I'm going to move on. Okay. So here's the general advice. So I've given you 3 different ways to prove an implication type of theorem statement. I think I think it's most natural to think about the direct method first. So assume the hypothesis is true and see what you can do with it. Is there a definition that you can write down that's related to the hypothesis? Is there some equation that you can manipulate to make it look like the consequence? And then see if you can play around with it. After using that little bit and playing around with it, if you feel yourself getting stuck and not getting closer and closer to an answer, then another approach you can take is to ask what would happen if the conclusion is false. So you started with thinking about the hypothesis, see if you can get to the end. Okay. This is the hypothesis. Then you're kind of wandering around all of the infinite mathematical things you could do from that hypothesis. If you feel like you're not getting closer to the answer, if you're stuck at a certain point, then you work backwards from opposite of conclusion, so negation of conclusion. And then see if you can come to a clash. See if there's a contradiction somewhere. And then see if working backwards gives you something that conflicts with what you've done so far. And then see if you can end up with either a conclusion, contradiction, or maybe a contrapositive proof. Okay, so this is a standard technique, is to kind of go from both ends. And sometimes it's much easier to do one direction or the other. Sometimes both directions work. Sometimes one direction is much more straightforward than the other. I should warn you a little bit. So you are a beginner of writing proofs, there is a tendency that the beginning proof writer tends to write down contradiction proof frequently. And I have to give you a warning. I think when you're doing this method of working forwards and backwards, I think it tends to end with a contradiction proof that makes sense to you after struggling with the problem for a little while. But when you come to a contradiction, ask yourself, like, step back a little bit and see if you can recast the theorem as a direct proof or contrapositive proof. Because usually those structures are much simpler to read at the end. In fact, some mathematicians hate contradiction so much that you say, hey, don't ever write contradiction. You could always recast it as one or the other. They're kind of right, but I also kind of think contradiction has its place. So it is okay to write down contradiction proof, but take the time to ask yourself if you can make the argument a little bit simpler. And a lot of times it can be. Okay. All right. So moving on from just implication, let's look at if and only if statements. So if you have a situation where you want to prove something, these two things are equivalent, or something is true if and only if something else is also true, you could break those type of proofs into two implications. So I think the most standard way is to consider the implication and its converse. So prove the two directions you can go, from hypothesis to conclusion, and conclusion also implies hypothesis. So if you can go from P to Q and Q to P, then you have this if and only if statement proved. Another way to go about it, which is equivalent, is to go forwards, but also the negation also goes forwards. So P implies Q, and not P implies not Q. So this is the contrapositive of this statement. So these two are equivalent. So you could do either of these things. They're both fine. Another way you can go about proving P if and only if Q is to kind of look at half of your proof. So maybe you can show that P implies Q, one of the directions. And then ask yourself if every step of the way was this statement true if and only if the next statement is true. So if each step is shown to be if and only if, you can go back and forth. Then you could just say that at each step and then show that the two things are equal. So that sometimes shorten up the proof because you don't have to write both directions. Okay, let's move on to proving things with quantifiers, like universal quantifiers and existential quantifiers. So when dealing with quantifiers, usually one direction of the proof is much easier than the other. So for example, if you have a universal quantifier, it is much easier to disprove universal quantifier than to prove it, because for you to show that universal quantifier holds, you have to check that it's true for every member of the domain, right? So there's a couple different ways you can go about it. So In a rare case where the domain is finite, there's only finitely many things to check, then maybe you can do that. Just plug in, make sure every case holds. But you can't do that if the domain is infinite. You don't have time or room on your piece of paper to check infinitely many cases. So in that case, you have to resort to a general argument. And possibly breaking up into cases. Maybe you can use one argument if x was an even number, and maybe you can use another argument if x is an odd number, things like that. So you could break it up into cases, but all of the cases put together have to cover all cases for the domain. So an example of what I want to tell you is Goldbach's conjecture. So every even integer greater than 2 is the sum of 2 prime numbers. So this is a universal statement, right? Every even integer greater than 2. So that's the domain, even integer greater than 2. And then show that if you have that, then you could write it as the sum of 2 prime numbers. So this is a conjecture. So a lot of people believe that this is true, but no one has a proof for it yet. In fact, it's been shown experimentally, all the even numbers up to, let's see, 1,000, million, billion, trillion, quadrillion, quintillion. So 4 quintillion up to 4 quintillion, even numbers have been checked to be sum of 2 prime numbers, but we don't know for general. There's still infinitely many numbers left. So checking by example does not equal proof. I thought that was interesting. So let me know if you find a proof. Okay, opposed to those type of universal statements, showing the negation, something doesn't hold for all, is much easier. So by easier, I mean, it's, if it's true, then you can just kind of just provide one example. And the example you can show that it fails for is called a counterexample. So here's an example statement that I'm going to disprove. So let's say square of any integer is positive. That's a statement. And because of the phrase that's used, any integer, this is a universal statement. There's infinitely many integers to check if you want to show that this is true. But if I'm trying to prove this is false, I just have to come up with one example where this fails. And in this case, this is a false statement. So you could just provide one counterexample. So 0 is an integer, and 0 squared is 0, which is not a positive number. 0 is not positive. So if I give one example where this universal statement fails, the whole statement is false. So I'm done with that. That's called counterexample. Okay. Another thing that's difficult is the negation of existential quantifier. So it's not the case that something exists. So here you have to check if fails for every possible x in the domain, or you have to use some kind of generalized argument. So let me give you let me give you an example of theorem and a proof that I really like. I think this is a very beautiful theorem and a proof. So let's look at the theorem that square root of 2 is irrational. So this sounds like a direct statement, but the word irrational means there isn't a ratio of integers where you can write it down and it's equal to square root of 2. So you could interpret this as non-existence proof, that you can't write it as a ratio of integers. So let's see how this could be proved. So suppose there exists two integers p and q such that p divided by q is equal to square root of 2. And if you can find these integers, you could choose it in such a way that they don't have common factors. Right? So if they have a common factor, like 3, for example, you can kind of divide away the common factor and reduce it. So suppose this is in simplest terms and has no common factor. And then from this equation, you could square both sides to get this equation. So square of square root of 2 is going to be equal to 2. And if you also square the other side, you get p squared over q squared. If you multiply q squared to get this q squared over to the other side, here's an equation you would get. 2q squared is equal to p squared. So here I'm using a fact that I haven't proved yet in this class, but I hope you'll forgive me for using this. If p is even, then, well, p is even if and only if p squared is even, right? And p is odd if and only if p squared is odd. So I'm going to use that fact. You could see that the left-hand side of the equation is even. It's 2 times some other integer. So that means that p squared is even. And if p squared is even, then p itself is even. So since p is even, I could write it as 2 times an integer for some integer k. And once you substitute this into that equation, we get this equation, 2q squared is equal to, in parentheses, 2k squared. If you square the right-hand side and simplify a little bit, you get q squared is equal to 2k squared. But this means that q is also even, right? Because q squared is equal to an even number. And that could only be true if q itself is even. Okay? So q is also even. But this is a contradiction because p and q were chosen to not have any common factors. No common factors because we reduced it. But that contradicts with the fact that we just deduced that they're both even. So they both have 2 as a factor, common factor. So you can't have a common factor and not have a common factor at the same time. So this is a contradiction. And the only thing we assumed was that square root of 2 could be written as a ratio of 2 integers. So this must have been false to begin with. Therefore, square root of 2 is irrational. I think it's a really beautiful proof. In fact, I like it so much that if you go to Canvas, the Canvas image is this proof right there. Okay. All right, so one more proof that I want to show. So negation of existential quantifiers showing that something doesn't exist is a difficult proof. But existential quantifier argument in the positive direction is actually pretty easy. You have to give an example where it's true. You just have to find one element where the statement is true. So here's another theorem that I really like. It uses the previous theorem that we proved. Okay, so here's the theorem statement. There exists a rational number expressible as irrational number raised to an irrational exponent. So, okay, let's prove it. By the previous theorem, we know that square root of 2 is an irrational number. In fact, that's the only rational number that we know in this class so far. So let's consider square root of 2 raised to the square root of 2 power, okay? So I actually don't know if this is rational or irrational, but it's either one or the other, right? So if square root of 2 raised to square root of 2 is rational, then we are done, because that was the theorem, right? There exists a rational number expressible as irrational number raised to irrational exponent. And this would be it, because root 2 is irrational. If it's not rational, so if square root of 2 raised to square root of 2 is irrational number, then now consider a different number. That number raised to square root of 2. Right? So both inside of the parentheses and the exponent is irrational. But if you simplify this expression, exponent number to an exponent itself being raised to an exponent is the same thing as multiplying the exponents together. But square root of 2 times square root of 2 is equal to 2 in the exponent. And the base is now square root of 2. So root 2 squared is equal to 2. And 2 is a rational number. It's a ratio of two integers, 2 divided by 1, which is rational. So, okay. This is a little complicated structure of the proof. So if this thing is rational, we're done. If this thing is irrational, then this thing is equal to rational number. So either way, you have an example where you have an irrational number raised to irrational number is equal to a rational number. And that's the end of the proof. I really like this proof because it kind of, it's like the proof itself doesn't tell you which of these is the correct answer. It turns out that the second one is the example that works. The root 2 raised to root 2 is rational. Sorry, it's irrational. But that takes, that's a little bit harder to prove. But it kind of gives the reader, like, you have two choices, but one or the other, you have at least one example. So we got it. I really like that. Anyways, this is where I'm gonna end my video. And I'll see you guys later.